Okay, here we go. So, when I do all that, I get 11,240. So, Q is 11,240 joules. So I'm skipping the math. You're just multiplying this by 0.2. That's how we do all these neutralization. I don't care what acids and bases they give you. Find the moles. And remember we did one last week where it was like a 2-to-1 ratio. But it doesn't matter because it will react in the proper proportions to make the salt water. So if you remember that problem, let's say this was 0.2 and 0.1. Right, let's say it was 2-to-1, you would always use the bigger number because you would still be actually reacting 0.2 moles, you would just have two of them. So 0.1 and 0.1. So anyways, I'm just reviewing that concept. If this year you have one of these and it's not 1-to-1, just use the mole, use the greater number of moles because they all need to react. And that's what you would multiply this by, turn it to joules, and again, that's positive. Why? Because these two are giving off the energy as they react, so the water they are creating actually absorbs that energy. So it's a positive value for the water, right? So it's 11,240 equals, we're solving for delta T. It's 200 grams because that we assume the density is 1 gram per milliliter, like pure water, even though it's not, we're just assuming. So 200 grams is the mass, 4.18 is the specific heat of water. The delta T is 13.44. 13.44, that's my delta T. The initial temp, I forgot to write it, was 22.5. Sorry. 22.5 degrees, that's my initial. So I have to add those two numbers, 22.5 plus 13.4, right? Because 13.4 is equal to the final temp minus the initial 22.5, so I add that. So it's 35.94. 35.94. So I think these are harder. Hopefully this year if they give you one of these, or a combustion, they give you all the numbers you need and you're solving for this, right? So if they give you the mass, they give you the change in temp, you can solve for Q, then all you do is divide it by the moles, and that gives you delta H. That's how you would do that. So I've tried to show you all the different ways they could ask the same thing, right? Solving for delta T, solving for final temp, solving for delta H. We've done those, whether you remember it right now or not. We've done an example of each one. So, and the combustion, burning something. So hopefully you're good with that. All right. Next, chapter 18. So grab your books, open them up to those problems, and here we go. All right, I'm going to go to page 823. You don't have to. I'll just write down. I know you guys can read. So what does that mean? It means if the test gives you the reduction potentials, or you need to use this chart on homework or something, I know you can read the numbers, right? So I'm not going to make you do it. Hopefully you already did anyway. But here's how we do number 23. So we have Mg solid plus Zn plus 2 yields Mg plus 2 plus Zn solid. So what we need to first identify, and I didn't say this to the whole class the other day, I'll say it now. The further left, what does that mean in terms of oxidation and reduction? I said it yesterday for those of you who were here, maybe you can remember. All right, let's go back to Regis Chem. What did we learn about group 1 metals? Most react. What did we learn about group 17 nonmetals? Most react. So the way it kind of works is you start at 1, start at 17, and as you move kind of towards the middle, the reactivity of both of them decrease. So as you go left to right, your metallic properties and anything metallic becomes weaker because those are really good metals on the left, and then as you get to the middle, you start getting to the metalloids, which is kind of like half metal, half non-metal, and then you cross over and you're all non-metal. So as you move left to right, all metallic properties, including reactivity and oxidation and all that stuff, decrease. And then non-metals, it's the opposite. As you come this way, they're less non-metallic. So magnesium is in group 2, zinc is in group 12. In terms of chemistry, magnesium is a better metal. Yeah, sure, zinc we use a lot in like real life for coating metals, making them galvanized screws, nails and stuff, usually coated in zinc. It doesn't react with the air as much as steel. We don't do that with magnesium because it's way too reactive. So where am I going with this? Back to my original question. Who's more easily oxidized, magnesium or zinc? Magnesium. So group 1 and 2 love to lose their electrons. So do all metals. But as you move towards the middle and the right side, they're less willing to lose electrons. What number or word tells us that? There's actually 2. One is the amount of energy needed to remove an electron. The other one is the desire or attraction for electrons.
Ionization energy.
Ionization and electronegativity both decrease as we move to the right. Meaning, they don't hold on to their electrons as much. I said that backwards. They increase, because of the nonmetals. But the metals, it's the opposite because of the effective nuclear charge. I probably just confused you. Sorry, guys. My mind was going too fast there. Let me back up. Group 1 and Group 2 are really reactive. What does that mean? They like to be oxidized. If you were to go to table 18.1 on 823, the Group 1 and Group 2 are all the way down near the bottom. They are the best oxidizing oxidizers. Up at the top, you have fluorine, you have oxygen, you have these over here on the right side. So the point I'm trying to make here is, can you look at this reaction? So after all that rambling, can you look at Mg plus Zn plus 2 yields Mg plus 2 and Zn? Can you tell me who's oxidized, who's reduced, without even looking at the electrons? So that's a goal that I would like you to have before you take this test is, can you just look at a reaction and base where they, depending on where they are, you can say, oh, that one's oxidized, that one's going to be reduced. That was the whole point of all that rambling. So really, I can look at this and say, oh, that's oxidized, and the zinc over here is going to be reduced. How do I know that? Because zinc is not a very good metal. It's really far to the right. So this is what happens. Mg gives an electron, and if we were going to go backwards, then it would be this direction, right? If we're going backwards, but that's not favorable. That direction is. So after all that, that's what's going on. We have 2 moles of electrons, and what is the question asking? What is the equilibrium constant? So we need to first find this from table 18.1, then we need to find this, then we can find K. So this is the first thing we do, second thing we do, third thing. And I went through this yesterday, so you guys who were here, it doesn't hurt seeing it again, but just, stay with me. E cell is equal to the E of the cathode minus E of the anode. Delta G equals negative NF E cell. Delta G, oops, that's an A, is negative RT, natural log of K. So there's my thought process. And I know I'm going fast because I got to get to concentration cells here. These numbers will be and have to be provided to you. Have to be. Or the test would just straight up give you that. They might say, given the following reaction in a galvanic cell, the E cell is blah, 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 calculate equilibrium constant. So they may give you that, then you use this equation, then this equation. So if we look these up on 823, the cathode would be the zinc. So that is negative 0.76 minus magnesium is negative 2.37. So that's my E cell. So when I do that, who has that number for me? What is it? 1.61 volts. That goes in here. Faraday's constant is 96,500. N is 2. So my delta G would be negative 2 times 96,500. And what is it on your sheet? 485? 485? Yeah. I'm not worried about that too much. Remember, E cell is positive if it's a favorable, thermodynamically favorable. So a battery, a voltaic galvanic cell set up correctly, that should be positive. This is always going to be a larger negative number. Anodes are always a larger negative number. Cathodes are smaller negative numbers. That used to be a trick when they gave you the reduction potentials. They don't give it to you anymore. So I still talk about it, but it's not really relevant. Not really. It will be if they give you a whole list. When we get to electrolytic cells tomorrow, we'll come back to that concept of the more negative number. But anyways, the cathode minus anode accounts for that, and that's why it's always going to be positive. If this number is a bigger negative every time, this will always be positive, because it's a negative minus a negative. All right. So when we calculate delta G, we get they use the shortcut equation, which I don't really teach because I don't think it's good. I think it's good to practice each one, so if you need to solve for that, you know how to do it. You can put this all into one equation, and that's what they do. Who has a delta G for me? What is this?
Negative 310,681.
Yeah, again.
310, 681.
Okay. And that should be joules. That should be joules, which is good because R is 8.314 joules per Kelvin mole. So now we take this number, and it's going to be negative 310,681 divided by negative 8.314 times, what's the temperature? 298? 298, which is equal to the natural log of K. So really it's E raised to the, and this is the positive number, right? So E raised to that, whatever that is, and that gives you K. It's an enormous number. 3 times 10 to the 54 is what the book says. Which is what we want. That's a good battery. That's a good cell. So this is how you do every single voltaic galvanic cell problem. It just depends what do they give you. They could give you the K and ask for E cell, right? You could do it kind of in reverse. They could give you the K, you solve for delta G, you need to figure out the moles transferred, and then you can solve for E cell. And then they could say, okay, based on your number to E cell, is this thermodynamically favorable or not? Well, if it's a positive number, it is. If it's negative, then it's not. So when I'm doing this, I've done this all year. You should be used to me at this point. I just think of what they could ask, right? So they could give you any combination and then ask multiple questions about that. Questions on this? So I'm going to go faster on the next ones that are basically the same thing. Okay, 24. The answer, they just want the E cell. 0.368 volts. So that's thermodynamically favorable. What do they give you? Oh, here we go. I totally forgot, but this is exactly, so they gave us K. So I apologize, I'm not going to go through this problem. They give us K, you take the natural log of it, multiply by these, get your delta G, plug it in here. Now the only thing is, you had to understand N is 2, because it's SR and MG plus 2 and SR plus, it's just like this, except it's SR with MG. Yeah, so it's 2. 2 goes in here. So it would be the exact same thing, except you are solving for this. You're solving for your E cell, and it's 0.368. So that is thermodynamically favorable, which, SR is lower on this chart, meaning a more negative number here. And that's not a bad thing to remember. You got a lot to remember, but the more negative the reduction potential, that's your anode every time. Okay, 28. What is going on here? Oh, this one. Yeah. Did anyone Tactus? Anyone think they have an answer for? Well, you know what? Let me. I need the ability to stop time. That's what I need. Does anyone else wish they could do that? Some of you go to bed at like some ridiculous hour every night. Don't you wish you could stop time, get your work done, and then go to bed?
Yeah.
Normal people. It is what it is, I suppose. Let's get through it. All right. Okay. So why was this hard? Cal, why is this a hard problem? How come? Okay, let's get perspective. 23 and 24 might have been hard at the time, but now that we went over those, why are those supposed to be easier than 28? How about that's a better way to say it? Mm-hmm. It's confusing because it's just one element. So you got 2 Cu positive 1, so it's worth me going slow over this because it's confusing. All right. Do we have any homework? Oh, the thermal quiz is due Friday. Is that it? That's all we got going on right now? Good. Okay. So, what's happening here? And I wrote in the picture or the remind, I tried to give you a little hint. So, essentially you have 2 of these, right? One of them's doing this. Oops, that's not true. Let me restart that. So they have sorry. One's doing this and one's doing this. What's going on here? How do you go from a +1 to a +2? Who's losing an electron? Liz, you with me?
Yeah.
Yeah. Who's losing an electron?
Copper.
Right. So oxidized. It's losing 1 electron. What's happening down here? This one is gaining an electron. That's reduced. If you know that, now you can find the E cell, because E cell is cathode minus, this is our anode, anox, red cat. Now you can subtract. They gave you the reduction potential for so they gave you the E for the reduction, which is 0.52 volts. Yes. So now, how does that help, right? So that, hold on, make sure I'm doing this right. So that's this one. This is 0.52 volts. That's my E for this one. So how does that help us here? How do we find the E cell? So E cell is going to be our cathode minus the anode. So this is going to be 0.52 minus, right? What's the other number? What do we look up? So now I'm going to make you go to page 823. So everyone go to page 823. What are we looking up on page 823? Like, how do we know what the other voltage is, right? This is our cathode, so it's cathode minus anode. What are we looking up here? Where the heck is it? There it is. So I'm not trying to trick you here. We're looking for this. There's 2 half reactions going on. I did them for you. That was just starting to go over this. This one was provided. They gave it to you in the problem. This is the other one. This is my anode, my oxidation. That's the one we're looking up. Now remember, on the reduction potential sheet, if they were to give you, and they may, on a problem like this, they may give you like 4 of them, right? You got to pick out the right one. So this is what we're looking for. It's going to be it's this except in reverse. Copper +2 gaining electron yields Cu+. So I know some of you are probably like super confused right now, so let me back up. If you're given an overall reaction, they want to know E cell, you have to be able to write the half reactions. So you need to be able to look at this and figure out, okay, who's losing, who's gaining electrons. This is weird because this is doing both. It's called a disproportionation reaction. That's what it's called. The one element or ion is doing the same thing, or doing two different things in the same reaction. So one of these is losing, one of them is gaining. Yeah, that's weird. That's why I gave it to you and want to go over it. Again, just so you're aware this can happen. So anyways, I think everybody found this at this point. It's 0.15. So this is 0.15. So 0.52 minus 0.15, we get 0.37. So E cell is 0.37. E cell 0.37 volts, so it is thermodynamically favorable. Okay, now what is it asking us to solve? All the other fun stuff? Yeah, alright. So, for the sake of time, even though I'm running out of time, I'm not going to do the calculations with you guys. You can do that. It's really just how do you. I know from being a student, I still remember the feeling of I don't know how to start this. I don't know what to do. Like I don't even know what's going on. Like I understand that feeling. So that's what I explained. This is how you start it. You write your two half reactions. You find the E cell. Then you go from there. You use delta G equals. Now, how many moles of electrons are there? That's another thing we need to understand. Just one. It's normally 2. When you see this, it's usually 2, but you're starting with a +1, so it's only 1 mole of electron. So N is 1, Faraday's constant, 96,500, 0.37 for your E cell. There's your delta G. Oh, that's negative, sorry. Then you use the other one to find K. So you can do the math, I know you can. You just have to get to that point. All right, and then the picture. I'm going to go over the picture right now, but I'm trying to remember what it was. Oh, it's from my notes. All right. All right, so tomorrow we're going to do concentration cells. Who did the picture, but who did it, but feels confident they got the right answers? Anyone? All right, you okay? What'd you get for E cell? Okay, try again. Anyone else get a different number for E cell? 0.43. Okay, so you should be able to get the right answers. Yeah, I think maybe you flipped it, Nicole. Maybe. And sorry, did I sound rude? I didn't mean to be rude. So write this down somewhere. Remember it. I don't have time to do this. I want you to do that again for tomorrow. 0.43 is the E cell for that picture that I sent. You guys all know what problem I'm talking about. It's silver with water. 0.43 is the E cell. Solve for delta G and K. But I want you to try and get the 0.43, right? That's just the answer. Don't just take it and go. Try and figure out where that came from. All right. All right. So that's it. Tomorrow we are going. The goal for me tomorrow is to finish electrochem. So you better lace them up tomorrow. We're going fast.
This is when somebody says that if I start
Who's not gonna be here?
Wait, McCoy, are you playing tonight?
Yeah, I'm excited.
I can't tell this.